A pair hidden Markov model compares two DNA sequences at the same time. It explains their differences using three hidden states. The model contains probability rules. They describe how likely it is to stay in a state or switch to another one. Each state produces a different alignment event. The match state emits one base from each sequence. If the bases are the same, the probability is high. If the bases differ, the probability is lower. The insertion state emits a human base and a gap. The deletion state emits a mouse base and a gap. The algorithm creates a memory table. Each cell stores the best score for a position and state. The algorithm visits every possible position. For each position, it tries every possible state. From every position, the pair HMM can make three possible moves. A match aligns one base from each sequence and moves diagonally. An insertion consumes a human base and leaves a gap in the mouse sequence. A deletion consumes a mouse base and leaves a gap in the human sequence. Together, these three moves allow the model to build an alignment between the two DNA sequences. Previous score, transition, and emission combine into new score. Each move receives a score. The best scoring path wins. The DP table remembers the best score. The back pointer remembers where it came from. When the search reaches the end, the highest scoring final state wins. The algorithm follows the stored arrows backward. This reconstructs the best hidden state path. The pair HMM has found the most likely evolutionary alignment between the two DNA sequences.